Allais paradox. Next, we want to talk about the Allais paradox. On the right-hand side, you see Maurice Allais, who came up with this thought experiment. Consider the following setting. You have the choice between two lotteries. Lottery 1 pays 1 million with certainty. Lottery 2 pays 1 million with a probability of 89%, 5 million with a 10% probability, and you end up without any money with probability 1%. Which of the lotteries do you want to take? In setting 2, you again have the choice between two lotteries. The first lottery, you get $1 million with a probability of 11% and $0 with a probability of 89%. The second lottery has the following payouts. You get 5 millions with a probability of 10% and 0 with a probability of 90%. Which lottery would you select? This is a very famous experiment, a thought experiment, and the observation is that most people go for the first lottery in setting 1 and for the second lottery in setting 2. However, this contradicts expected utility theory, as you will see on the next slide. So again, let's try to write down the problem using a model. If you select lottery 1 in setting 1, it has to hold that your utility from getting 1 million with certainty is larger than the utility you get from 5 millions with probability of 10% plus the utility from 1 million with probability of 89% plus 1% times the utility you derive from 0. Okay, so whenever you select lottery 1 in setting 1, this has to hold. Now let's look at the second setting. If you select lottery 2 in setting 2, which most of the people do, it has to hold that 11% times the utility you derive from 1 million plus 89% times the utility you derive from 0 is smaller than 10% times the utility you derive from 5 millions plus 90% times the utility you derive from 0. So this has to hold. And expected utility theory tells us that we can just add and subtract utilities as we want. So we can also rearrange this statement to get the following. So by adding on this side 89% times the utility of 1, if we add this on both sides, what we get is, and subtract 89% times the utility of 0 on both sides, we get the following. So we get the utility of 1 is smaller, or has to be smaller than 10% times the utility of 5 million plus 89% times the utility of 1 million plus 1% times the utility of 0. However, what you can see is that these inequalities contradict each other. So if you compare it, you see that if this holds, this cannot hold. So this was the, let's say, mathematical proof of the Allais paradox. On the next slide, we will look at a more graphical example. Okay, so what you can see here is I tried to illustrate the setting, the lotteries, as a draw of urns. So you have 100 balls in an urn, and when you have 10 red balls, 89 green balls, and 1 blue ball. And if you're looking at lottery or setting 1, it means that the first lottery implies that when you draw a red ball, you get 1 million. If you draw a green ball, you get 1 million. And if you draw a blue ball, you also get 1 million. However, lottery 2 implies that if you draw a red ball, you get 5 millions. So in case a red ball is drawn, you're better off with lottery 2 than lottery 1. If a green ball is drawn, it's the same if you took lottery 1 or lottery 2. And if a blue ball is drawn, then lottery 1 is better than lottery 2. If you do the same illustration for the second setting, what you get is that if a red ball is drawn, you get 1 in lottery 1, 5 million in lottery 2. If a green ball is drawn again, this is the same. And if a blue ball is drawn, you receive a higher payment in lottery 1 than in lottery 2. If you now compare these two settings, you see that you should take the first lotteries if you prefer 11% times the utility of 1 million over 10% times the utility of 5 million plus 1% times the utility of 0. The settings, setting 1 and setting 2, they only differ in the consequences of drawing a green ball from the urn. So this trade-off is always the same, and the only difference is given by what happens if a green ball is drawn, but the green ball has the same consequences for both lotteries in the respective settings. So you can see that here is a clear contradiction, because this trade-off should make a difference, and this trade-off, if you decide that 11% times the utility of 1 million is better than this one, you should always take the first lottery, and if you decide against it, you should always take the second lottery, but you should not switch between lotteries. And this cannot be explained by risk aversion, for example.